Hello everyone and welcome to the channel. This channel is all about system design concepts but with a slight twist. Instead of discussing various whiteboarding ideas and functional requirements, we would actually look at building production systems and see how they interact in real time. Today, we'll be concentrating on the classic URL shortener system design problem. But like I said, instead of discussing various functional and non-functional requirements, we'll actually look at building the URL shortener with a few different strategies. If that sounds interesting to you, stick in. I have divided this video into three different sections. First, we will be designing a simple URL shortener application using just SQLite and Python, and here we'll focus on a couple of implementations to actually generate URLs and then see how they fare against collisions. We will also be talking about concepts like simplicity and scalability and discuss trade-offs between both of them. Secondly, we'll extend this solution using MongoDB, Sharding, and also build a Redis caching layer. This would help us scale this system a little bit more. And here again, we'll be discussing about trade-offs between complexity and see how the system scales. Finally, we'll look at how the data is actually distributed in various shards across MongoDB cluster. Let's dive in. Okay, this is a very simple application that uses Python and SQLite. So we have basically two APIs. One is for posting a URL and it will take in the long URL and return us a short URL. The second one, we post the short URL and then get back the long URL. Easy peasy. Let's look at the insert URL method here. It takes in the original URL and then a method to generate a hash. So we basically have two methods here. Before we even start the hash, we check for the existing URL if that is present in the database. If not, then we proceed with the hashing method. First, we use a SHA-256 hash and then only take the first 6 digits of the hash, and this is then again checked in the database for presence. If it is present, then we don't do anything, we just return that back. If not, we insert that and then return the response back to the user. The second and the default method is the nanoid method. This uses a Python's library called nanoid, and this generates 8-digit unique URLs which are very unique, and we'll see in a second how it is collision resistant. So let me see how this works out. So we actually have a server up and running. Like I mentioned, I have used uvcon here. Let me go and run the curl command. And you're able to get the original URL here. If I do a curl get and I try, okay, so I did the get here. Let me do post. So let's try 1 2 3 4 5 and you are getting a short URL. Let me do the get using the short URL again and see what happens. R69 C P. Yeah, there you go. You're able to get the example 1 2 3 4 5. As I mentioned at the start, this is a very simple application and it does not have a lot of scalability because we are using an internal SQLite database and it's not built for scalability. There's also a small collision script that the AI tool came up with, and this is able to check collisions in various methods that we are currently implementing. So the short hash method that's currently being used, let's see how collision resistant that is. Yeah, as you can see, I was running a million iterations and you're able to see collisions pretty quickly. Let me try it again. Yeah, so I'm trying it a couple of times and always it resists, it brings up collisions. Let me now change this method and actually use the other method that we were using. And now if we go here and it's running a million iterations. So let's just wait for a second. So it's good that, so yeah, there you see, it has not found any collisions. In the next section, we'll actually look at a larger application which uses MongoDB and caching. Okay, so in this section, we are planning to extend the URL shortener application and incorporate a few more components. So as you can see, we have a cache layer, which Redis is helping us with that. We also have a sharded Mongo database, and we will see how that actually works and see how it's actually sharded. So if you walk through a small flow, when there's a new post API where a user wants to create a short URL, we first make a call to our cache layer, and if that value is present in the cache, we just return it back. But if that is not present, then we actually generate a new hash, a short URL, and then store it in the sharded Mongo cluster. And at the same time, we also store it in the cache. The arrow may not be pointing towards that, but that's what happens. Now, if you want to look at the sharded Mongo database, I have another diagram that I have put through. So this is actually how the sharded Mongo cluster is set up. So as you can see, there are a few components here. First one is the Mongo S. This is actually the router that takes in all the requests and routes to various shards depending upon load and other parameters, and also depending upon the shard key. This is the config server, which actually stores Mongo's configuration in terms of how many shards are there, how many replica sets are there, and also a few other metadata. And at the bottom, you see are 3 actual shards. So each shard has been deployed as a replica set, and each shard also has 3 replica sets. So let's now walk through the code. There are a few files going on in there to sort of support all of this that I just described. The app.py is the main file. Again, you can see there are 2 APIs. So there's the get API for getting the short URL, the post API that is actually to post a long URL and then get back a short URL. This is the nano method that we saw in the previous section. It's same. Again, we see that there is a fast API that's used to actually host this application as a web application. There's actually 2 objects that we have. So one is the URL database, which is actually the Mongo database. So here you can see we first get a Mongo client, and then we actually connect it to the Mongo database using these particular values. This also has an environment variable, so you can configure it and you can send it however you are building or orchestrating your systems. You will be easily able to inject environment variables here. It's also setting up a sharded collection here, and it also adds the URL shortener collection, and then also creates a couple of indexes in order to sort of optimize the database operations. And then we actually have a class to sort of have a few repository methods. So it's find by original URL, find by shortcode, and then actually the insert URL. And then finally, we have a helper method to show the sharding status and what the shard is. We'll cover this in detail in the third section. Then if you look at the cache layer, again, as I mentioned, we are using Redis cache here. First, we get the Redis client, we connect it. Again, environment variables here, you can inject it however you like to. There's a TTL, which is determined or set by default to 3600. And then again, this is a helper method that just checks if the client is available, and it returns none or null if not. Then we get the shortcode, get original URL, and also do a set, which is for setting a new value or a key value inside the cache. So if you go again into the app.py and just check the workflow at the post request. So first, when a user calls in, the default method is nanoid for generating a short URL. Then we first check if the existing URL is present. This is actually kind of a neat way to also avoid caching or producing a same sort of short URL for any URL that the server has already seen. So it also stores both the small URL and also the long URL as a key value pair. So we first check that, and if that is present, then we immediately get the shortcode and return it back. So we don't even have to call the database to find one, right? And then if not, it calls the database. If there is an existing URL, we send it back. We also set that to the cache. Finally, this is the scenario where the system is seeing this URL for the first time. So we choose how to hash this URL. If it's a hash method, we use this. If it is the different one, we use the nanoid method, and we then generate a shortcode, write it to the database, write it to the cache, and then return it back. Similarly, the get URL checks the cache first. If it's there, it returns. Otherwise, it goes to the DB, find by shortcode, and then it actually gives us back the URLs. So let us now see how all of this works in the action. So I've used Docker Compose here just to sort of bring all the containers in together. So I've used a network that all the containers used, And as I said earlier, there are quite a few containers running here. There are 3 shards, and each shard is sort of deployed as its own replica set. So we have all the volumes that are mapped. So this is the Redis container, Portainer, which we'll look at in a second. This is the MongoOS router, and these are actual shards that are sort of present in the Docker Compose. So if we quickly check, I've already sort of deployed this, and you can see there's quite a few containers that are running. Let's go to Portainer here, and you can actually see that there are containers running here. This is the Mongo router, this is the config server, Portainer, which is actually this is Redis, and then this is the shard. And I think again, let's try curl and -x, and if you post this, and you can get the short URL. So as I mentioned, it is the nanoid method that's using, so that's why we get an 8-digit short URL. Let's actually do a get, and if you see that, and there you go, you're able to get this. In the next section, we'll actually be looking at the shard distribution and see how the data is actually stored inside the shards. See you then. Okay, in this section, let us look at how the data is actually distributed inside the shards. I have a test Python script here that does a few things. Actually, it does not do a lot of things. It just calls the app.py container that's connecting to the Mongo and the Redis, and then sends a bunch of different requests. There are also other sort of flags here. One is the method to choose nanoid or hash. Nanoid is the default. You can also configure host and port and a few other things if you want to add that. Then it makes requests to the Python application. It generates a random URL here, and then also generates a lot of shortcodes, and then finally prints us a small level of telemetry or metric saying that how much each and every request took and what was the average time. Let's just quickly see how that works. So all the other containers are running, and this container is starting up. So it's processed the first 100. It's taking a bit of time. Usually it does not take that much. While this is running in the background, let me go through a few things here. So I also have a small Docker command here that actually goes into the shards and actually gets what the collection is and how the data is stored. It then saves into the JSON file, and here you can actually look what the values are. So currently there are 3 shards and the replica sets are there, and you can see the number of documents that are equally distributed. I also have an index.html file that the AI agent kindly came up with, which uses chart.js to actually do a visualization. Let's see if that actually completed. Oh yeah, it finally completed. It took quite a while, so took around 50 seconds. I think maybe because I am doing a screen share and explaining, that's why it takes time. Otherwise it takes fairly less amount of time. So we can just go back. So this was the previous one, and you can actually see that it finished in much faster time. So it only took 9 seconds, and the average request was 45 milliseconds, and here it was 250. So like I said, let us look at the data distribution in the shard. So in order to do that, first let's run this command, and you will see that the value in the shard distribution.json will be changed. It's actually querying the shards. Yep, that's done there. And now it's 900, and you can see there are 1000 documents here. Let's now use Python again and see. Oops. Let's run this in 8001 port because we have something else running on 8000, and yeah, there you go. So you should now be able to see all the documents. So shard2 replica set has 1000 documents, and you can see this shard2 replica set has 1076, shard3 replica set has 1009, and shard3 replica set has 1009. And then so you can see that Mongo is able to distribute this data, in a very orderly fashion, and it's able to balance data across shards. So in this video, we went through the URL shortener system design problem, and we saw a few different things. We first saw a Python application and a couple of different ways in which you can generate short URLs. We then extended that design and used MongoDB, shards, and caching to sort of implement a much more complex system using Docker containers, Docker Compose, etc. We also saw the actual data distribution inside the various shards and replica sets. If you like watching this video, I hope you try this, and I am going to post detailed instructions about how to set up your environment in a blog post which will be linked down below, and I'll also push this code in GitHub, and again I will link this repository URL in the description as well. Thank you so much for watching, and see you in the next one.